For example, I was waiting for the elevator today, and there's a seminar that's going on here at Ohio State, and you're going to be learning a little bit about what it means to collect research data, then present that research data. There's two ways that a chemist will typically present their research data. The first one is to go to a big conference, and you can do one of two things at a conference. You can give a talk, which is typically anywhere from a 15-minute to a 45-minute PowerPoint presentation on your research, or you could also give a poster session or make a poster, which is what you guys are going to be going to do later in the quarter with your real project. In this case, there's a graduate student here in the chemistry department that's looking at various transition metal complexes, and the complex that was on that's going to be centered around this talk that could be a potential anti-cancer drug is RuBipy2L2, where L is probably a generic ligand like chloride or something like that. So the first question is, what on earth is BIPY? All lowercase letters. That is not an element on the periodic table. But what that is that this complex is one of these ligands. And various ligands we looked at, say, ammonia. So if I have NH3, and I draw that ammonia with my lone pair down here, it's going to be, its VSEPR, or electron domain geometry, is going to be tetrahedral. So it looks something like this. And we say that these ligands are Lewis bases or electron pair donors. So however many electron pairs a particular ligand has, that's how many bonds that it can form with a transition metal. Ammonia has one lone pair. So if we're going to make an octahedral complex with ruthenium and ammonia, we can fit 6 ammonias around that transition metal center. This Bipy ligand, though, is known as Bipyridine. And if you look on page 1031 of your textbook, there's a table that has all the common ligands. And it classifies them as monodentate or polydentate. This Bipy ligand is actually a big, large molecule compared to this NH3. So the molecule that is formed here, if you look in your textbook, is going to look something like this. And it's going to have these rings right here. This is the way an organic chemist would draw bipyridine. Each of these vertices right here that I'm putting little dots on is going to be carbons. And those carbons are going to fill their octet with hydrogens, which we don't draw. And then we indicate these nitrogens right here. The key point for this ligand is that, remember, these are electron pair donors. When you have a nitrogen and it's an sp3 hybridized nitrogen, it's going to have a lone pair pointing out just like this. So in this case, since this particular ligand has 2 nitrogens, when it bonds to a transition metal, it's going to form 2 bonds to that transition metal center. We call this particular ligand a bidentate ligand. And if I were to try to surround a bidentate ligand around a transition metal center, I can only get 3 of them on there. But by putting 3 ligands around a transition metal, and if these ligands are bidentate and each of them have 2 lone pairs, it's going to give a coordination number of 6. Okay? So this RuBipy twice L2, since this Bipy right here is bidentate, it's going to occupy 4 coordination sites if there's 2 of them. Plus we have 2 ligands that would be monodentate type ligands. So this complex right here is going to have a coordination number equal to 6, which tells us that this is an octahedral molecule. So all of the bidentate ligands in this chart are going to occupy more than 1 bonding site. The common ligands, or the common bidentate ligands, are En, which is ethylene diamine. There's Bipy. There's Phen, or phenanthrene. And there's a wide variety of these ligands on that table. There's even this ligand that we call EDTA, which is this big, huge molecule that actually has 6 parts of that molecule that will bind to the transition metal center. So if you have an EDTA ligand bind to a transition metal, it's going to give a coordination number of 6, even though we only have 1 of them. And there's a picture of that in chapter 24 of your textbook. So keep that in mind when you're going through and you're trying to calculate the coordination number for a particular transition metal complex. You'll be responsible for all the ligands on page 1031 of the textbook, so make sure you look through them. And more importantly, count the number of lone pairs that you have on that particular ligand, because that's going to give you an indication of how many bonds or how many binding sites it's going to take up in a particular transition metal complex. Okay? So this page right here in the text with that chart, very, very, very important for you to indicate what the coordination number of a particular ligand is.